Hi, everyone. I hope you're doing well. Beautiful sunny day here where I am. Um, Today, we're going to start our next section of the course, and we're going to introduce quantum mechanics in 3 dimensions, or we'll use quantum mechanics to talk about 3-dimensional systems. You'll see that the rules all remain pretty much the same, but things will get a little bit more complicated mathematically. That being said, we're going to restrict ourselves to just a few problems, the ones that are the most important. In particular, something called a particle in a 3-dimensional box and the hydrogen atom, okay? That's really the goal of our discussion. Today, we're going to start out just by reminding ourselves how things work in 3 dimensions, and then introducing the 3-dimensional wave function and Schrodinger's equation in 3 dimensions. After that, we'll turn to our first example, the particle in a 3-dimensional box, okay? So it'll be interesting. Just pay attention because there's a little more details going on now that we have to keep track of. Here, well, let's turn to the notebook. Okay, we're going to start talking then about quantum mechanics in 3 dimensions, but let me just fix this 1 second. Okay, quantum mechanics in 3 dimensions. Let's start by reminding ourselves of some classical quantities in 3 dimensions. Things like position, momentum, angular momentum, kinetic energy. So in 3 dimensions, of course, the position is represented by the position vector, usually r, which we can write as x in the I direction plus y in the j direction plus z in the k direction, okay? So this is a vector in 3 dimensions. And denotes the point at coordinates x, y, z. How about momentum? Well, momentum is also a vector with an x component, y component, and z component. Excuse me. Okay. How about angular momentum? Remember how angular momentum is defined in classical mechanics? Think about it for a second. We learned this back in physics 1, but formally it's defined as r cross p, and it's also a vector. And finally, let's write down a formula for the kinetic energy, okay? Of course, the kinetic energy is just the magnitude of the momentum divided by 2m in non-relativistic systems. And so we can write this as px squared plus py squared plus pz squared. That's the magnitude of the momentum squared, and then divided by 2m. Okay, so not so bad. Remember, we have to use vectors in 3 dimensions for position, momentum, angular momentum, and so on. Now, let's see how we can write the wave function. Actually, the wave function doesn't really change. Only now the amplitude of the wave function depends on position in 3 dimensions, not just in 1 dimension. So now the wave function is a function that has an amplitude at every point in 3-dimensional space. Okay? And the probability density which tells us here the probability to find a particle within a volume dV located at point R is just the absolute value squared of the amplitude of the wave function times the volume element dV. Okay? And the probability to find the particle in some location of space, let's say in some volume of space, oops, perhaps here, is just given by the integral of the probability density over the volume. Okay, where the triple integral denotes an integral over a volume. In Cartesian coordinates, we might write this as, I'm sorry, I'm going to have to erase part of my drawing here. We might write this way. This would be an integral over x, y, and z of the probability density, which is a function of the coordinates x, y, and z, and then times the volume element, which would be dx, dy, dz. Oops, excuse me. Oh dear, not sure why it's doing that. There we are. Okay. And then we have limits. Okay. So that's the wave function adapted to 3 dimensions. And finally, we have Schrodinger's equation adapted to 3 dimensions. And here, I'm just going to give the time-independent Schrodinger equation. That's what we've been using most recently, and that's what we'll focus on now too, okay? So this is the time-independent version, and we can write it as in the following way, minus h bar squared over 2m. And now we have the second spatial derivative of the wave function, but now we have to take partial derivatives in each direction. D by dx squared of psi plus d by dy squared psi plus d by dz squared psi. And that's equal to, as before, I'm going to go to the next line, sorry. And that's equal to E minus U of R times psi. Okay? It's convenient to adopt a shorthand to use the operator del squared to denote second spatial derivative with respect to x, y, and z. Maybe this is familiar to you, but in any event, it's just a shorthand, okay? And if we do that, then we can write this equation more compactly as minus h bar squared over 2m del squared psi is equal to E minus U times psi. So that's Schrodinger's equation in 3 dimensions, okay? And now this is a partial differential equation in 3 variables, x, y, and z. Or if we choose to work in another coordinate system, say spherical coordinates, they might be r, theta, and phi, or whatever, okay? But it's a more complicated equation to solve. All right, well, that's the basics. We've reminded ourselves that in 3 dimensions, we have to worry about vector quantities. And then we've introduced the wave function, and we've introduced the 3-dimensional Schrodinger's equation. Let's stop here.